ANOVAs. More ANOVAs. Hello. So I am going to go through a very long, detailed, step-by-step way to compute by hand a repeated measures ANOVA with a single factor. It's called time. And what we're going to assume is we're going to pretend that we recruited 5 participants. And for example, participant 1 gave us a score at time 1, at time 2, and again at time 3. And participant 2 likewise gave us a score at time 1, time 2, and time 3. Same for participant 3. Their scores are in row 3, participant 4 in row 4, and participant 5 in row 5. So what we already have, because I had the pleasure of computing with this same data between subjects, one-way ANOVA, pretending at that point that this fake data was from 15 participants, 5 from this group, 5 in this group, and 5 in this group. We're not doing that this time though. We computed all these somewhat together, and what this is 1.8 is the mean of these scores, so the time 1 mean, 3.2 mean for time 2, and 7 is the mean for time 3. And then this here was computed by looking at the within subject variance and computing that for each of these times. And what that means is we said, okay, so here's the first score. The mean of this group is 1.8. So we want to know, like, how are the scores in each of the time groups? How are those varying amongst themselves? And so we go 1 minus 1.8. We square that, and then we go 2 minus 1.8. We square that and add it to the first thing, and etc. So 5 times doing this and adding them all up after squaring them. Then we get 2.8. And so that is kind of the within subject variance, if you want to call it that. And the reason we did that beforehand, the reason that we're going to keep it here, is because it helps to compute sum of squares error. So 2.8 happened coincidentally, or maybe not, maybe I did it myself on purpose, I don't know, to be the within subject variance for time group 2 or time 2. And then 90, just because these numbers are a bit larger and they also deviate from their mean quite a bit more, we ended up getting a larger within time or within group sum of squares for this. The other thing that we don't use this bottom line, but the other thing that I thought would be helpful to look at is the variance in each group. So as I said in the other video, and I will say again, feel free to kind of look up the formula or try to guess it for the variance of a group of scores. Knowing the mean is essential, and I computed it by hand just beforehand, and I put that value there. So the variance, or in other words the square of the standard deviation for the time 1 scores, is 0.84. I also got 0.84 for time 2. For time 3, a bit more variance, quantified by this 4.74. Okay. Here we had the information that we needed to compute a between subjects ANOVA, but now we want to kind of compare and contrast and learn the within subjects ANOVA, that mechanical process that running it through software would not allow us to have. So to do that, I require a marker. Okay, so the first thing that we need, that we didn't need in a between subject scenario, and I will do this a lot, I'll kind of try to compare and contrast because I think that might help, is that we need to consider that each of these people are different people. So each of these these rows are provided by 5 different people, so we need to take that into account when we look at analyzing the variance of the effect for the time versus maybe the effect of different people being different. That's something that within subjects or repeated measures can help us to do. So the first thing to allow us to do that then is we have to find the subject means. They're participants, but sometimes we say between subjects design, sometimes we say subject means. We don't mean to dishonor our participants by not calling them participants. We're just lazy, and participants is really hard to say and write, you know. So these means then, what you would do is instead of looking at how we did the time means, you would look across and you would compute the mean for this person for all the 3 scores that they gave us. So we would go 1 plus 2 plus 1 and divide that by 3. And if you think I'm going to do that in my head, you are mistaken. So if I'm going to round to 3 decimal places, I'm going to get 1.33 for participant 1. And the next mean then is going to be a 3.33. And if you want to try these 3 means just to kind of actively do it on your own, please feel free, pause the video, go ahead. Okay, cool, you're back, awesome, hopefully you have these, and I will write the rest of them down. And again, they're not perfect, they're rounded to 2 decimal places, so they look a little ugly. When you're faking data, sometimes that can happen. 5.33 for participant 4's 3 score mean, and then finally 6.33 for participant 5. So this is a really nice illustration of how different people are different. Everything was done the same in time 1, time 2, and time 3 respectively for each of those 5 participants, but whatever it is our manipulation was, I'm leaving it to the imagination because I'm too lazy to think of an actual scenario. You end up seeing that participant 5 here has a rather higher mean than, say, participant 1. And so with the fake data, you can kind of see that not only are there changes as we go and look at the means for each of the times, there are also changes as we look at the means for each person. So that's something that is new to the process of looking at a within subjects or repeated measures ANOVA that we did not look at explicitly when we did a between subjects ANOVA. So the next thing that we're going to want to do is we're going to make note of our grand mean. The grand mean is oftentimes denoted by x bar for mean with 2 dots at the bottom. And what you could do to compute this, there are several ways. The first go-to way would be to add up all these 15 observations and divide by 15. If you want to try that now, go ahead. There's a cheater way that you can do too. And the reason, and the only reason why you can do the cheater way, is because there's 5 observations in every single one of these 3 groups. In other words, the ends are equal across the times, you could say. Or something that we get into too is calling these cells, and so we would say that the cell sizes are equal if you want to sound fancy. And that lets us take the mean of this number, which is the mean for time 1, this number, and this number, mean for time 3, and then divide those means by 3. You'll still get the grand mean. Finally, there's another way. You could take the means of these 5 numbers. I don't think I said it wrong. I said means. Mean. It's one mean. It's 5 numbers. You add them up and divide by 5. And if you do that, you'll get a little bit off probably because of the rounding. But in the end, I'm going with a big old 4 for my grand mean, whichever way you decide to compute it. Cool. Without further ado, we have down here already for our use the sum of squares total. The sum of squares total is the same process as with a between subjects when we ANOVA, where we look at all of our observations and one by one carefully we take each of the scores and then we subtract the grand mean, square it, and then add the same thing with the next score, same thing with the third, fourth, fifth. Here's the 12 more that I'm just leaving out in the illustration here. So we would do that. We would go here to time 2. We'd go 2 minus 4, square that, write that plus that, and then we'd go 4 minus 4 squared, add whatever that was. I know what that is. And same with this score minus 4 squared, this score minus 4 squared, blah, 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 right? You get the idea. I tend to belabor points just because I try to do a very like slow, I'm not going to try to say careful job when I do this. So yeah, I mean, speed ahead if you need to, please, by all means. Don't just stand there getting annoyed and irritated. Okay, oh, sit, whatever you're doing, lying down. So the sum of squares total when we do this procedure is 168. And so please feel free to check that. Maybe I made a mistake. If I did, apologies, but we'll go with that number just for understanding the process here. So the first thing we're going to do, now that we have the grand mean, and then we'll keep this on the side because we might need it later, is we're going to compute the sum of squares for the effect, or the SS groups, as you might be used to calling it from the between subjects one way. And that's the exact same thing that I did when I went through a between subjects. But this time we're just going to call it SS time. It's still SS group because these times, they're like 3 different manipulations. The same way a group 1 and a group 2 and a group 3 would be 3 different manipulations. So we can still call it SS group, but to be careful as we go into more complicated designs, we decide if it is a within subject manipulation, we just call it SS time, kind of a shorthand. So to do that, you need the formula for that. Now, if you want to call it SS effect, you can do that too, I'm sure, as long as you're being clear to all your readers and so forth. So the formula for that is little n times the sum of, we start with a group mean, or a time mean, or whatever we're calling it, and then you're going to subtract grand mean from that, square it, and then repeat the process adding each time. So if you did this, it's going to give you the same thing as with between subjects. It's just that we're calling it SS time instead of SS group. So you should get the same thing, but we'll do it just to be sure. So how many observations per cell do we have? We have 5, so little n is 5, so 5 goes here. And then we're going to, I found a mistake in my notes. That's kind of part of why I got all weird and like, I don't know, debilitated. Yeah, I got worried. I'm like, why did I do that? I put a 4 here. Do you see this? There's a 4. I don't know if you can see this, but this is wrong. Okay, so anyways, that's fine. I'll just recalculate it in my head. So we have 1.8 minus 4 for mean of time 1 minus the grand mean, and then we're going to add to that 3.2 minus 4, we're going to square that 2, then we're going to add to that 7 minus 4, and we're going to square that 2, and then close my big bracket so that everything is multiplied by 5 in the end. Just to simplify that, so 1.8 minus 4 squared, I have it in my book already, is, so I have to be careful because I don't want to copy my mistake. Okay, 4.84, did you get that? I hope so. If not, that's cool. You're possibly correct. It doesn't matter as long as you get the process. And then 0.64 for group group 2, and then 9 for group 3, and then this is already squaring these differences, and then so we end up getting 5 times whatever that is, and that is 72.4. Okay, so it's good. See, we caught my like weird mistake. So now what we need to do is that there's like an extra thing. Okay, so let's pause for a second. When we had a between subjects design, we never really computed these subject means. They didn't really matter. They didn't make sense. Each individual score was from a different person, right? So then if we only had this, and then we did our SS of the effect, which we would have called SS group, then we would have gotten 72.4. And the next step, can you think about it? The next step would have been to compute, I would have computed the sum of squares error. Or, yeah, no, that's all, or a sum of squares within. Sometimes people call it that. It's all very nice to have like a bazillion different ways to say the same thing. Welcome to math. And so anyways, I would have computed that, and I would have either added these up, because these are each kind of a portion of the SS error, because this is the within time group 1 variance, and this is the within time group 2 variance, and within time 3. And so SS error would manually just result in you adding these 3 up. Or since we have SS total this time computed beforehand, we could have just gone, I'm just going to do this. This is like kind of, I'm going to erase it. So that's why I'm like, just kind of for fun, just the thinking, is that you would go, if it was a between subjects ANOVA, we'd go SS total minus SS whatever this is, group, and then that would equal the SS error, which would be essential to us doing the computation. This is where the two procedures really start to diverge. So we're not doing that. All right. This is what we're going to do instead. We're going to find a quantity that allows us to capture the variance due to the fact that these 5 different people are different people. A fancy way to say this to impress your non-psych friends is the baseline individual differences. So next, we're going to find SS. So there's various ways, again, to denote this. Okay, so the between subjects could be one subscript to use, this is just the baseline individual difference. Okay, differences. I hear some like stuff going on. Sorry if there's a bit of background noise. There's an individual in my house who's stress baking right now. So that's a great idea, right? So they're doing that, and so like they're making noise. So yeah, please pardon the thing. So yeah, so we have this is a new feature of an ANOVA that we never needed when we had a between subject design just like this. So the way that we do this SS between subjects, or I think I'm just gonna call it like SSBWSS or something, I don't want to call it SS between, that's confusing. So I'm gonna just do this. I think it's very important that I belabor this point, because if we choose a way that makes sense to us to write these various quantities, explaining it to whoever is reading your work, marking your work, that is extremely helpful to us. So if I just wrote this, you'd be like, what the hell is that? Right? Why is there a little SS and a big SS? I don't get it, right? So so this is going to be my baseline individual difference, the sum of squares. And the way that you do that is, so there's a neat formula for that, and it goes K times just thinking. This happens sometimes. Sorry, thinking. Okay, times the sum of each of the subject means So subject means, I'll call it. I'm sure there's a better index for it, but that got me really stuck. I didn't pick one, so I'll just call it sub for the subject means. And then we subtract the grand mean from each of those. Okay, we square those, and then we sum them, we multiply by this k. Now, here is this interesting point. Because when we did the time computations, because we did that, each of these means, 1.8, there it is, 3.2, and 7, which made these three quantities, each of those had 5 observations contributing to it. That's why we used n, or 5, to kind of say, okay, this is the mean, but because it came from 5, we want to amplify it by 5, and same with this, and same with this. That's what this 5 does. So this k here, this has to do the same kind of idea for this SS between subjects or baseline individual differences. So if each of these subject means comes from 3 different time observations for the same person, then instead of 5, you would multiply, once you get this quantity, that number by 3 to kind of amplify this by the 3 observations that contributed to it. Not sure if that makes perfect sense. One way would be to try to explain it to your cat or stuffed animal or what have you, and try out loud to explain it, see if it works. If not, you can like contact someone. Anyone, just post it on Facebook. I need help, I don't understand. So what we're gonna do is we're gonna put the 3 here, and then we're gonna open up a big bracket, and then you know what we're gonna do? We're gonna somehow fit everything we need in here, because I've decided that that's what's going to happen. I forgot to put my summation sign. Oh no, yeah, I don't need a summation sign. I was right the first time. Oh, I'm so nervous. Okay, so then, okay, we're gonna start with subject mean 1.33 for participant 1. We're gonna subtract the grand mean. Notice how we're always subtracting the grand mean. I'm gonna square that, and then we're gonna go find our subject 2 mean, or participant 2 mean, pardon me. Subtract the grand mean from that, square it. This is the challenge that I'm giving myself, that I have to stay in the row. So then we have 3.67 minus 4 squared plus 5.33 for participant 4 rather. Blip, 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 minus 4 squared. I can't. Okay, so plus, we're gonna just stick it down here, plus the last person mean, 6.33, minus the grand mean, square that, close my bracket. Okay. So that's how we do these baseline individual difference variance quantities, or SS, between subjects, or whatever you want to call them. And so we're going to have 3 times whatever this is plus whatever this is, and I'm going to write that out for you. But why don't you like compute it yourself? If you make like computational errors, this might be a good time, because I have to erase the board. Yeah, so yeah, I'm just gonna do this thing. So yeah, or work ahead, or like try to, maybe you wanna get a snack, I don't know, and stuff. Okay, so we did this is 72.4, so we'll put this up here now, and then we're calculating this, so like continued SS between subjects, and that's equal to 3 times, and then I will do the next step in that computation for us right away. Not right away, like not quite now, but like right now. Okay, so when we do this simplifying of each of those squared bits, we get a 7.13 plus a 0.45 plus a 0.11 plus, ran out of room again, 1.77, and finally the last bit, 5.43. Okay, and when we add all those together and then multiply by 3, we end up getting 44.67. Okay, that's helpful. Now we have a sum of squares that represents the variance that is due to the fact that we have these 3 different times, which was the way that we designed our experiment. So the manipulation that we made is responsible for this 72.4 amount of variance. It's a unitless quantity. And then here we also have that 44.67 is the quantity that we would associate with the variance due to the fact that each individual person is different. So when they come in to the study and provide their time measurements, some of them are just going to be like higher than others in general. For example, this person had relatively low scores. We don't know what that means, if it's good, bad, whatever. No judgment. And this person had relatively higher ones in comparison. And so this is the kind of the awesome part of a within subjects or repeated measures design. What it's doing is it's saying now that the same person provided the 3 measurements as opposed to before when it was each individual score was in each individual person, we can account for the fact that different people are different. That doesn't have to contribute to the error variance. That can be removed, or some people, to be fancy, say it can be partialed out. So when I want to compute my error, we talked about this a bit before. We said that if it was a between subjects design, we would go SS error is equal to SS total, subtract SS group, which of course we're calling SS time now, to make sure we understand that we're talking about a repeated measures across some times. But now what we're going to do is it's the wrong color. Okay, so for the SS error that we very much need, we're going to go SS total, and then we're going to subtract our SS time, or the way that we would do it, SS group from before, SS effect, if you will. And then we're also going to subtract the baseline individual differences, which is just people kind of in a systematic way sort of being higher scored or lower scored across these rows here. The reason that it's not an error really, it's not just some weird noisy occurrence, it's the fact that people are different, and we can kind of control for that in the calculations. This is not going to fit. I'm going to make it fit. Minus SS between subjects was my shorthand for that. So the way we would do that is we're going to take our SS total. That's 168. Then we're going to remove the effect, obviously, right? So that's SS times, so 72.4. And then we're also going to remove this type of variance due to the baseline individual differences, fancy, 44.67. That shouldn't be part of the error. We would love that to not be part of the error for between subjects, but that doesn't make any sense. So that's why it's a fundamentally different setup. So when we do this computation, I won't say we, but I get 50.93. Don't know what you guys get. Maybe I made a typo, but this is the process, regardless of whether we made a tiny typo. So we have our SS error, and we have our SS effect, and that's called SS time, and those are the two SS's, or sum of squares, that we are going to then use to get our mean squared time, or mean squared effect, and our mean squared error. And then we'll be able to do some fancy division and get our F statistic from that for this repeated measures design. So I'm gonna I'll just challenge you or ask you kindly to give that a try, right? So we have this quantity here. In order to find the mean squared error, we need something else besides the sum of squares. What is it? Can you determine it? Think about that. Same for the SS time. And yeah, I'm just gonna put that quantity here for us. I just think enjoy wasting your time. Okay, so I'd like to have everything here. So this is 168. Unless my working memory is worse than usual. Okay, whatever. Oh yeah, it is. It's right there. And then SS time. So our effect, that will create the top part or the numerator of our F test. You can't see me, just my hand. That's weird. So that's 72.4. And then SS of the between subjects variance, or the, you know, like baseline individual differences. So that's 44.67. Okay, so we have that. So try and work ahead. This is a good idea for you. But you know, I mean, if you've just been focusing for forever and you just want to see the end, you can, you know, go ahead. Like just skip ahead, and then we'll get you to the finishing part of the exercise. It's the sum of squares that takes a while, and also just trying to understand this new sum of squares and what it means. That's taking us a while. All right, so open this marker. Okay, so for our computation, now that we have these sums of squares, we don't really need this. This just helped before, so it's no longer needed. I know that it seems as necessary as the SS effect and the SS between subjects. And then, oh man, what was the error? I forgot to write that down. Okay, error variance is equal to 50.93. I'm getting tired. Can't imagine how you're feeling. Hang in there, almost there. So that's no longer needed, but we need these three things. No, we don't. We don't need this either. No longer needed. So, why is this no longer needed? Well, just like with SS total, it helped us to get the sum of squares error, but now that we have the sum of squares of the effect, which is the time that they provided their observation, and the sum of squares error, which is everything that's left over that like doesn't really have to do with the fact that people are different, or this manipulation is causing a difference, the error. We already found that. So we just need this and this going forward. So the mean squared for the time is going to equal sum of squares time over, I'd asked what is the next quantity that we need to get to this mean squared? Well, we need the degrees of freedom. And the degrees of freedom time, if you're not sure, just think back to what you did for a between subjects design. Pretend for 1 second that this is group 1, group 2, and group 3. You'd say, oh, there's 3 groups. So degrees of freedom for that is 3 minus 1, or 2. So you do the same here. How many times were there? That's the same question. There were 3, and the degrees of freedom is then t minus 1 or k minus 1 from before. So that's equal to 2. So that's 3 minus 1, which is equal to 2. Okay, so on the bottom. So then we would say 72.4 divided by 2, and that is equal to 36.2. And this number here is the same number that we got, and you would get, if it was a between subject design. It still is the same numerator as a between subjects design. The difference comes when we compute the denominator for the F statistic, which we will do right this minute. The mean squared error, which can also be called like the MSE, like that, if that's a quotation mark, okay? So it's up to you, whichever way you want to call it. Just be consistent so we don't confuse anybody. That's going to equal the sum of squares of the error, or the error variance, and we're going to divide that by the degrees of freedom for the error. And the degrees of freedom for the error, that's tricky. We need help. We need help for that now. Okay, there's a formula for this. So this is kind of one of those tricky ones. I'm going to say it whenever you have a within subjects design or anything fancier. Try to appeal to the formulas for the degrees of freedom of the error. If you can, like if you had to memorize everything, there might be a different trick you can use, but it's so easy to just say, oh, well, the total degrees of freedom is capital N minus 1, or 14, and I know that my time degrees of freedom is 2, so maybe this degrees of freedom error is 12, but it's not anymore, so I'll show you. It changes. So the formula, it's a single formula, is n minus 1, where n is the number of observations per time, times, we'll say, k minus 1, where k, as we used before in a computation, is the number of observations per person, number of observations per time, 5, number of observations per person, 3. So that's going to equal 5 minus 1, oh yeah, that's awesome, times 3 minus 1, and so that's 4 times 2, so 8. It's not 12, it's 8. So yeah, that got pretty messy pretty fast, but so this is another kind of main difference, that when we are doing a within subjects design, we end up kind of needing to appeal to a formula, or again, there might be like a way you learn that's better, that's cool. This was the way that I thought of, so whatever. But see, the idea is that the degrees of freedom have to kind of reflect the fact that we for the error, we removed the individual differences, the baseline individual difference variance, so it changes the degrees of freedom as well. So now that we have this 8, we can compute our MS error, or MSE if you like. Sum of squares error is, in my circled area there, 50.93. We're dividing it by 8. If this is a between subjects ANOVA, it would be 12, as we discussed. And so that is equal to, I'm getting 6.37. Okay, so then we have mean squared error, we have our mean squared time. How do we compute the F statistic? So mean squared error, I'm gonna stick it up here, 6.37. And this is going to be 36.2. And then I'll just make myself some room. Now that we have that out of the way, we can just compute our F statistic, which is MS time divided by MS error. Just had more room, so I put this up here, but actually the time goes on the top, as you know. See, I made my own mistake. 36.2, okay, divided by 6.37. And what do we get for the F statistic then? That is 5.68. The end. Except it might be nice to know if this F statistic represents that at least 2 of the times differ. So we can look at our F crit and find out what that is. So if we were going to write the result in a nice format, we would have F. We put the degrees of freedom of the numerator, or the time effect, which would be 2. And then following that, the degrees of freedom error, which in this case are 8, is 8, R8, whatever, I don't and that was equal to 5.68. F crit can be found in an F distribution table, as you might be used to using, or when running in a software. The software has much fancier tables that are programmed into it, so they can also do that computation themselves. But for our purposes, you would have to look for your degrees of freedom numerator 2, degrees of freedom denominator 8, and you're looking at the table that represents alpha equals 0.05, and you would end up getting, well, I got 4.46. Okay, since what we observed with the fake data is a greater value than the critical value, we can say that there is a significant effect of time from this fake manipulation that I invented. So the last thing I wanted to do, because this is great, we got all the way through, we did everything really super slowly, and assessed, when to use these different sum of squares. I had to think a little bit when, we finished using this one and all that. That's a good thing to kind of think through too. But if we had a between subjects design, so if was between subjects as opposed to this repeated measures or within subjects ANOVA, the F would be F at 212, and it would equal 4.54. I hope you can see this. If not, I'm going to be really sad. 4.54 is this number. And your F crit, because you'd have to look at a different place, you'd have to look at the row for 12 degrees of freedom in the error instead of 8, you'd get a different F crit, and that would be 3.89. So just seeing this kind of comparison, so this is if we had a between subjects design, and then this is our result from this process with the within subjects or repeated measures design. See here, the F crit's a little different. The result's a little different. This was still a significant result, it just so happened. So it just helps to kind of compare, contrast, think about that. So that's the full thing. And I will leave you with something to think about, which is, we never use the variances in each of these groups or time groups. And I find it interesting that this variance is so much higher. Well, I made it that way on purpose, but it's interesting. And so you might want to think about the fact that, okay, these variances are the same, but this is so much larger than these two. Could that pose a problem for being able to interpret the results of this repeated measures ANOVA, which is that F is 5.68, which is indicating a significant difference across the times? Could that pose a problem for the result to have this variance so much different than the others? So that might be something that you would learn going forward. That's it. Turning off the video.